Professor Priyaranjan Sinha Mahapatra from Department of Computer Science and Engineering, Kalyani University will be the speaker, and Mr. Subimal Kundu, Fellow CSI, will be the session chair. So, in fact, we are running slightly behind schedule. So, what I would do is this: I will not waste much of the time because we have a technical session 1 and 2, which is a parallel session, which will start from 3:30 to 5:30. That was initially planned, and I think we will start this session right away. And I would request Professor Priyaranjan Mahapatra to kindly start the session, please. Thank you.
Sir. Thank you. So I'm going to start. So is it visible? Hello?
Yes, sir, it is visible.
Yes, sir.
Okay.
Yes.
So my title of my talk is a little bit generalized. It's sort based on different algorithm paradigms with focus on computational geometry. I have prepared this title after getting the feedback from the organizer. So thank you for selecting me for delivering this tutorial, though time probably short one was. So this is the broad classification, the broad view of my sketch of my talk. Initially, I will give some normal definition of optimization problem. Then we will, in this part, we'll discuss different types of strategy to solve optimization problem. Then what is approximation algorithm, where the problem is not easy to solve, technically called hard. Then we'll call some, then we'll basically, since they told me to focus on some technique on computational geometry, then we'll just discuss some few results on computational geometry. And then I try to give you a flavor how computational geometry techniques are used to solve some problem, especially in facility location. So, and this is already known to everybody in mathematics and computer science. An optimization problem is the problem of finding the best solution from all feasible solutions. Optimization problem can be divided into two categories on whether the variables are continuous or discrete. An optimization problem with discrete variables is known as combinatorial optimization problem. So here we should keep a note that what type of optimization problem we are considering are combinatorial optimization problem, because the solution space of this problem is discrete. Whereas the people from mathematics are generally tackling problem under continuous domain. This is the main difference. For each combinatorial optimization problem, there is a corresponding decision version. Right? A decision problem is sometimes called as yes or no question problem, sometimes called as fixed size problem. And the main objective for designing decision problem of a combinatorial optimization problem is to solve T. That is, sometimes we will get it shortly that it is not possible to solve the given optimization problem directly. First, I will try to construct the decision problem so that we can solve the corresponding optimization problem. To make it more clear, so just it is a very well-known problem. This is called graph coloring problem. Given an undirected graph, G equals to V, D is the vertex set, E is the S set. A coloring of G using K colors is an assignment of K colors to each vertex in V in such a way that no two adjacent vertices have the same color. The vertex coloring problem asks whether it is possible to color G using a pre-specified number of colors. That is, a graph is given, and you know the number of vertices, and a fixed integer K is given. Now somebody are asking you that is it possible to solve this, or it is possible to find out to solve the vertex color problem using K color. What is the optimization version? An optimization version of this problem asks for minimizing or for finding the minimum number of colors needed to color a graph in such a way that no two adjacent vertices have the same color. Now, definitely, what is the fixed size problem? What is the decision version? And we have to keep in mind so that we can solve my original problem. So is it K colorable? Because why I am talking in this way? Because note that we are talking about combinatorial optimization problem in the sense that we know the solution set. Because for graph coloring problem, a little thinking will tell us that exactly minimum one color is required and maximum n. When it is a complete graph, n color, and when it is a graph without having any edge, one color is needed. So we know the solution set. So graph may be that there is a chromatic number, maybe 1, 2, 3 up to n. So how can you find it? Right? So how can you find it? A little thinking. I'll come into this point. There are some problems for which there is no deterministic algorithms which runs in polynomial time. So let us suppose there is a brute force algorithm where there is no constant in time, and infinite time will be given to you, exponential time will be given to you, and within that time you can solve the problem. Suppose this time is f n. N is the suppose n is the parameter, n is a function of v and e, but it's an a. Now, how can we solve it? Suppose there is an algorithm which can test whether it is k colorable or not, and it requires order of processing time. So first we call it with k equals to 1, then k equals to 2, then k equals to 3, and in this way, when we will get our first answer, yes answer, we'll stop. And that is the chromatic number, and that is the minimum number of color required to color a graph. That is the original optimization problem. Now, can you do something better? This is the always question generally asked, a common question in algorithm. Then can we do something better? Yes, we can. We can use a simple binary search. In what sense? Because the number 1 to n is already sorted. Find out the middlemost. And this number is j. And is it j colorable? Yes. Then at least we can discard other half from j equals to j plus 1 and to n. And if it is not k colorable, j colorable, then we will then not k colorable means we will discard the left half and only consider the right half. So this is just like we may not be so rather it will be better to confuse, to avoid that we can use our binary search in different way, not only whether it is less than or greater than. So that's why it's sometimes called as prune and search with pruning factor half here. So in this way, binary search can be used to find out the chromatic number, and definitely the complexity becomes order of log n multiplied into fn. And little bit if we just try to think that many number of optimization problem are NP hard, and in optimization problem we are either finding minimum value or the maximum value. So either we are finding the maximum value or the minimum value. For such problem, it is not possible to design algorithm that can find exactly optimal solution to all instances of the problem in polynomial time in the size of input and until p equal to np. Because p class means that p class of problem means that consider any problem that can be solved by a deterministic algorithm which runs in polynomial time. NP class means there does not exist any polynomial time algorithm to solve it, right? So now how can you solve such optimization problem? So first is the brute force method. Develop clever enumeration strategies guaranteed to find optimal solution, no guarantees on running time. That is your running time maybe. I think that is running time may be exponential. Second is heuristic, intuitive algorithm, guaranteed to run in polynomial time, but no guarantee on the quality of solution. We don't know whether our solution is very close or not very close. We don't have any guarantee. Sometimes it will give good solution, sometimes will not give good solution. So next choice is approximation algorithm. Guarantees to run in polynomial time, guaranteed to get a solution which is close to optimal, also known as near optimal. And what is the obstacle? Need to prove the solution's values close to optimal without even knowing the optimal value. We don't know what is the optimal value. Still, we are trying to, we will try to conclude that yes, my solution is correct, say 50%. Right? If the result is 100, it will be never less than 50. If my approximation algorithm is good, it will be suppose 90% correct result. Result will never less than 90, will never 80%. It should be 90, 91 up to that. So I'll just give 5 minutes to give a flavor how algorithms, how approximation algorithms are constructed. That is when so definitely if we exclude brute force or heuristic, right, the next course of action is to relax the requirement of exactness and polynomial time complexity. That is the brute force method. And another possibility is to stick the polynomial time complexity and allow close to exact solution. This leads to your approximation algorithm. Now I will give a little example, a small example, where how an approximation algorithm is developed. To narrate it, we'll take the help of vertex cover problem. In graph theory, a vertex cover of a graph is a set of vertices that includes at least one endpoint of every edge of graph. A graph is given. What is the vertex cover? Is a subset of edges, subset of vertices, so that if you consider if any edge, every edge must have one endpoint on it. Now, what is the optimization? What is the optimized version? The problem of finding a minimum vertex cover is a classic optimization problem in computer science, and it is typically example of NPR optimization problem that has an approximation algorithm. This is a very common example of when we are taking any class on approximation algorithm. Now note this. This is the vertex cover. This is not a vertex cover, but this is a vertex cover. Because if you consider this vertex, and each edge has an endpoint on it, right? So for this particular graph, this is a vertex cover, lowest graph, but the middle graph is not a vertex cover, right? Now, how a vertex cover problem is generally written? Instance the undirected graph G equals to V, feasible solution is subset C, subset of V, such that at least one vertex of every edge G belongs to V. This is a feasible solution because this is the vertex cover, a subset of vertices, so that every edge has one endpoint on it. So that every edge has one endpoint. Now, what is the optimization version? The value of the solution is the size of the cover, right? And we will try to minimize it. Otherwise, if we consider the whole vertex set, it is a vertex cover, but it is not of the minimum value, right? So, in any combinatorial optimization problem, there is some objective functions we are supposed to optimize. The approximation ratio of an algorithm is the ratio between the result obtained by the algorithm and optimal cost of profit. This is called the approximation ratio. What is that? So approximation ratio is the ratio, the value obtained by the algorithm, proposed approximation algorithm, and the optimal value. And I have already told that this optimal value is not known to us. This is the trick, and this is the hard truth, right? So if this is a maximization problem, this value is less than equals to 1. Why? Because definitely we will not able to compute the maximum. We will not able to compute the maximum value. When the ratio is 1, then AI equals to A star I. So AI will be always less than equals to A star I, and that's why the ratio will be always strictly less than 1. In contrast, for minimization problem, we will not able to find out the minimum value. So we will compute something that is higher than the mini solution of the problem. So that's why AI is greater than A star I. So ratio will become immediately greater than 1. So this is the approximation ratio, sometimes called as a relative ratio. So sometimes it is called as relative approximation factor. So for maximization problem, the ratio is less than 1. For minimization problem, the ratio is greater than 1. I only need this. Given a graph, now we will take the help of another definition called matching. Given a graph G equals to V, a matching M in G is a set of pairwise non-adjacent edges, none of which are in loop. That is a subset of edges such that no two edges share a common vertex. This is the match, right? So consider the graph. What is matching? A subset of edges so that no two edges share a common vertex. This is called matching. And what is called the maximal matching? A maximal matching is the matching M of G that is not a subset of any other matching. Or more briefly, or more elaborately, a matching M of a graph G is maximal if every edge in G has a non-empty intersection with at least one edge in M. So consider a subset M, consider a matching, and it's called maximal matching. Why is it called maximal? Because our solution is not unique. And it is a very common observation for optimization problem. The value is unique, but solution is not unique. Right? So this is a matching aim of a graph is called maximal if every edge in G has a non-empty intersection with at least one edge in M. Right? Now the following figure, this is not that. For this graph, this is the maximal matching. Why is it called maximal matching? Because if you consider this edge, each edge has at least one endpoint on it. This 3 and 4 and this 1. So the maximal matching. Here, same thing here. This number is the size is 2. This edge and that edge. And this edge will cover this edge, that edge, and this edge. And this particular edge will cover remaining all. Note that the solution, we should always keep in our mind that solution may not be unique, but value is unique. Right? Here also, this maximal matching is to this one. Right? Similarly, immediately I can tell you that this if this 2 also forms a maximal matching. Now question is, how can you find out the maximal matching? Input is the graph, is the greedy method, and greedy method is already known to everybody that means that always we are adding something with the hope that our solution will be improved. So solution can be looked as a vector having component x1 up to xn. First we will add x1, then we will add x2, and there is an important property of greedy method. Once added, there is no chance to correct it. Right? So here the input is the graph GV, a maximal matching is the output. And how can you compute? Initially C equals to 5, select an edge arbitrarily. There is no choice, you just select an edge. And C equals to C union UV. Remove all edges incident on U and V. So we'll delete all edges having endpoint U and V, and it just repeat this step 4, 5, and 6. Still all edges are removed. So what are we doing? Initially C is 5, and we are initially we will select an arbitrary edge, and there is UV. C equals to C union UV. Remove all edges of the given graph having endpoint either on U or on V. Now what we'll do? We'll repeat the step 4, 5, and 6 until we are deleting, we are removing all edges. Right? This is the output. Now, how can you find out that? This is your basically the I will tell you later. This is the approximation algorithm. And now I will explain how approximation factor can be computed. Performance analysis of this algorithm, the edges picked up by the algorithm is maximal matching. What I have told you earlier. Hence, C is the vertex cover. When it is maximal matching, all edges have some endpoint on it. So it is a vertex cover. The algorithm runs in polynomial time clearly because maximum we are deleting all the edges. So it runs on polynomial time. The optimal vertex cover sister must cover each edge in M. This is a very important observation. Hence, sister contains at least one of the endpoints of each edge in M. So at least the size of the edge with the optimal value should be at least. So sister must be greater than mod M because the minimum that is the maximal matching, that value should be at least greater than mod M. So how can you get? So now what is the output of our algorithm? Mod C 2 into number of vertices. One edge is contributing 2 vertices. So if there are M edges, what is the value? 2M. And what is M? M is less than sister. So though we don't know the optimal value, but we know my optimum value should be greater than the value of the match. So now C by sister is less than equals to 2. So this is your approximation ratio, and that's why it is a 2-factor approximation algorithm for the vertex curve. Right? So from the definition, this is AI, and this is C. So C is the A star I. So if we consider the ratio AI divided by AI star is less than equals to 2. So factor, it is a minimization problem. So the minimization problem, ratio should be alpha is greater than 1, property holds. So our algorithm is correct. So this is two-factor approximation algorithm. This is the simplest algorithm for taking this type of thing. Now, I know sometimes exam in theoretical computer science, especially in algorithmic classes, people are using this example style. What is the meaning of that? This is your basically complete bipartite graph. Complete bipartite graph means you can divide this edge into two sub-edges, V1, V2 up to Vn, and V1, V2 up to Vn, right? Where m equals to a, right? So I am considering it is a Kmn, like Knn here. There are n vertices here and n vertices here because m equals to m. So number of vertices. So sorry, number of vertices is 2m plus n. Since m equals to n, equals to 2n, right? So number of edges. V1 is contributing n minus, so it is contributing if you exclude it. So how can you compute the total number of edges? We can easily compute the total number of edges that there are n vertices and each having n minus 1 edges. So total n into n minus 1. There are two such possibilities. So that's why it is 2n into n minus 1. So to a little computation, we can conclude the total number of edges of the complete bipartite graph in this figure is 2 into n minus 1. And if we delete, following our earlier algorithm, how can you delete? If we delete a particular edge, right? What we are considering, if we go back to our algorithm here, considering edge, and we are removing all edges having endpoint here, right? That is our algorithm. So if we consider a particular edge, this edge, and if we remove the all edges having endpoint here, so easily we can compute that if we consider a particular edge, 2 into n minus edges will be removed. How? Consider an edge, right? Note that one particular endpoint is contributing, is connected with n minus by using n minus 1 number of edges. And another endpoint is also connected with n minus 1 number of edges. So total is 2 into n minus 1. So total number of vertices is 2 into n minus 1, and total step. So in each step we are deleting it. So number of steps required is n. So the size number of steps required is n, means the size of the maximal matching is n. When the size of the maximal matching is n, then the output is 2n. And clearly, what is the optimal value? It is n. Because this optimal solution is from the particular figure. This is basically C star. So since it is 2n, so that's why this example is called as a time. Right. Now, quickly, we will go on 25 minutes. Okay. So now we will tell something about geometric algorithms. Right. Geometric algorithms mean we will just conclude. We will tell you only three techniques. One is called line sweep. In line sweep algorithms in computational geometry, a sweep line algorithm or plane sweep algorithm is an algorithmic paradigm that uses a conceptual sweep line or sweep surface to solve various problems in Euclidean space. It is one of the key techniques used in computational geometry. And one important problem solved is the line intersection problem. Suppose there are n lines. I want to find out the number of intersections. In relative, what happens? The number of intersections is always very less than n square, because maximum number of intersections may be n square theoretically. Each line can intersect with a remaining line, right? So that's why people have started to invent another type of algorithm which is called output sensitive. Like if the number of intersection is k, then the time required is n plus k into log n. K may be order of n square, but the chance of k to be order of n square is very minimum. That's why this type of algorithm is becoming popular day by day, because our output complexity depends on the number of intersections, right? So that's why this type of algorithm is called output sensitive algorithm. This is a very common diagram used in image processing, facility location. It's called Voronoi diagram. How it is done? Consider some points on a plane, and what is the significance of it? If you suppose somehow we have computed this region. How can you compute? Very simple. That is, consider these two join to this line segment and and compute it perpendicular bisector. Again, join these two lines, computed perpendicular bisector. Join these two lines, computed perpendicular bisector. Where they all these three bisector will intersect, that will give this particular point. Similarly, so brute force way you can compute in this way, right? But these are the very crude way we are computing, keeping less importance regarding on the efficiency of the algorithm. In this lecture, there is not a scope to elaborate how can you compute it, but there is a good result which can help you to find it. And this is probably known to you. Fortune algorithm is a strip line algorithm for generating a Voronoi diagram for a set of n points in plane using order of n log n time and order of n step. So sweep to give most importance to the sweep line, because even I today I will discuss this one of my work, basically one of my research work it is, that is where we have used sweep line algorithms, and how cleverly we have also tried to show how cleverly we can use prune and search, right? And another important things are geometric data structure. Maybe these are known to you. That's why I visit it very quickly. Range tree, KD tree, interval tree, segment tree, right? And this is basically your one-dimensional range tree. If I want to find out the values lies between 2 and 30, 23, we can find it in this. We can only check their endpoint 3 and 24, whether this belongs to this group or not. Otherwise, your algorithm will give you, right? This for one-dimensional searching. And similarly, what is the complexity of it? Let C be a set of n points in a one-dimensional plane. The set C can be stored in a balanced binary search tree, which uses order of n storage space and order of n log n construction time. And this query may be reported whether such points are there or not in order of k plus log n. If the number of note that output sensitivity, because we don't know how many points will lie for a given range. So this is k. So k number of reported. Similarly, another is, and when the value of k is very high, it is the order of n, and when it's very small, it is order of 1. And similarly, as for two-dimensional range tree, that is sometimes rectangular range query is also there. That is here, this is data structure range tree is used. Two-dimensional range tree they are called frequent. We will call them frequently. Let P be a set of n points in the plane. A range tree for P uses n log n storage space and construction n log n time. Earlier was order n, this n log n. By querying this range tree, one can report the points in P that lie in a rectangular query range in order of log square n plus k, right? And this can be also reduced up to log n using fractional cascading, right? So, and now I will quickly visit some problem on facility location in computational geometry. In computational geometry, basically, we are using some geometric features of the object considered to increase the efficiency of the algorithm. It is always desirable to find an optimal placement of certain facilities to serve given demand efficiently. We'll explain later what is the meaning of optimal placement. Examples are storage facility, manufacturer plant, depots, warehouse, library, hospital, fire station, base station for wellness services such as TV broadcasting or mobile phone services. A customer can get service of a facility if and only the customer is within the range of the facility. Range of the facility refers to the distance to which the facility can deliver its service. There are some facilities like hospital, ambulance, fire station for which it is mandatory to facilitate each customer. There are some facilities which should be given to each customer, and there are some facilities which are narrated in this particular para. It is sometimes not possible to provide services to all customers due to financial cost. In such cases, the objective is to facilitate the maximum number of customers. Because now I am telling that this is the broad view. This is the broad view of research regarding enclosing problem, which is also called covering problem. What is mean? What is the meaning of this? Meaning is that suppose there before going there, I'll come back. I just quickly I will tell you like this. Suppose this is the point set. I want to cover it by a circle. So we can cover. Yes, we can cover by using less radius. Cover. Now we already know that it will be the radius covering all these points or enclosing all these points will have a property that radius should be minimum. Right? And it will only happen when this circle will pass through 3 points. Earlier 2 points is not passing it, right? Only 2 points. Then it is passing 3, right? So otherwise green color circle is not passing through 3 points. So this is the property. So this is the property we are using to find out. Is called minimum enclosing circle, MEC. So this is the geometrical characterization somebody has told that minimum enclosing circle will always pass through 3 points, right? And this is simply follow from the algebraic formula of circle directly, right? So similarly, suppose my range is rectangle like this. Notice here sides are parallel. This is parallel to x-axis. This is parallel to x-axis. This is parallel to y-axis. This is parallel to x. But this is the area. But then you spoke to minimize it. So it is not always right to give the answer for which the corresponding rectangle has sides parallel to x-axis. So these are the observations. So same points we can cover all the points using rectangle whose sides are not parallel to x-axis. So this is the right answer. This is not this is wrong answer, right? So now if we go back to this particular slide, this is the scenario of research in computational geometry where covering problem is considered. The problem is called covering problem or enclosing problem. Full enclosing means each point will lie within the corresponding geometric object. Where geometric object may be circle, in that case the point will be covered by the circle, and all points will lie either with interior of the circle or on the boundary, right? And this is called full enclosing problem, and definitely the radius will not be infinite and will be minimum. It's an optimization problem also, right? Similarly, the geometric object used in the literature is triangle, rectangle, polygon, non-convex polygon, right? Not only that, you can use more than one object, because if you consider your wireless problem, that is, I want to place my base station in different places, what will be my objective? One objective, because the radius is already fixed, because we already know the range of each base station, how much signal can travel. That will give you the radius of the corresponding circle. And what is my objective? And number of base stations we want to place, we know. That's why in that case, what is my objective? Our objective may be to reach each customer. So all points will lie within each circle. And another objective may be when the radius is given. When the radius is not given, and our objective is to enclose all the points, sum of the radius is minimum. It's common as the objective. Generally used in clustering also, right? So all these problems are hard problems. So we sometimes even finding the approximation algorithm to solve this such hard problem is also hard. So we should be cautious here, right? And another is the maximum. What I'm telling that sometimes the radius unknown. That is enclosing problem, partial enclosing, right? Because we are not enclosing whole point set, so maximum. So we will find out. We'll try to place a circle in such a way that the number of points enclosed by the circle is maximum, but the radius of the circle is given. Okay? So this is an optimization problem. Similarly, square can be given, rectangle may be given, but the size for this type of problem, their size of the corresponding geometric object is already given. Here only orientation of the object is given, but Our objective is to minimize the radius or minimize the size of the rectangle or the area of the rectangle or the perimeter of the rectangle. Right. Similarly, another important is sometimes clustering. In clustering, suppose I want to develop some clustering technique, but each cluster will always contain k points, not more than k. So k enclosing. So it will always enclose k points. So enclosing problem is something called k enclosing using circle, not by object. Right? So it will always enclose k points and the size of your circle is minimum. And how the size of a circle is determined? By its radius. So a radius will be minimum. Similarly, triangle, its perimeter of the triangle will be minimum. Perimeter of the rectangle will be minimum. Area of the rectangle will be minimum. So these are all different optimal criteria. All objects shown this vertical way is reflecting the current object using in this domain of research under computational geometry, especially under a subdomain of facility location. Right. So just how much time is there? How much time I have? 22 minutes. Okay. So
you can continue for a few more minutes if you want.
Okay. Thank you. So now, so I will now show you that how a problem of computational geometry is solved. And I especially focus on K enclosing problem using a square. Initially, researchers considered the K enclosing problem for computing a smallest axis parallel rectangle or square. Right? If you consider the square is the problem is a little bit different to it is rather easy to explain. That is, our objective is to find a minimum area rectangle square here so that it will contain k number of points. And these are the previous results, right? And also they have developed some algorithms when the k value is very large. Particular case, the value of k is greater than n by 2, less than equals to n. Specialized algorithms. But our cluster will contain more than n by 2 number of points. And this result was by Segal and Kaden, order of n plus k n minus k size in square algorithms. Right? And here we will basically our problem we have solved. Given a set p of n points in a two-dimensional plane and integer k is less than equals to n, greater than equals to, find a smallest axis parallel square including at least k points of p for large values. Right? So somebody has definitely this problem was not exactly studied or some algorithm was proposed. Next researchers will tackle the problem is supposed to design an algorithm whose time complexity is better than earlier. Right? So we are considering this problem. So square is axis parallel. We should keep it in mind and its size will be minimum. Area will be minimum, perimeter will be minimum because area equals to a square and perimeter equals to 4a. A is the size. Right? Now for this definition is equal. A square is called to be k square if it is containing k number of points, at least k points, and its size is minimum. Because you may consider many squares containing at least k points. Right? And we will consider or we will call that particular square as k square whose size is minimum. What is size? That is the area, that is the length of a side is minimum. So now this is the approach. How can we solve it? Again, I have taken the term like decision problem when we have explained about that is graph coloring problem. First, we will construct the corresponding decision problem. How can you find out the square, an axis parallel square containing k enclosing square whose size is minimum and the value of k is greater than 5. Then we apply prune and search technique as an optimization scheme to identify k square. I have already told that for combinatorial optimization problem, we know the solution space. Here we also prove it, and that is the solution space is this. And then after getting the solution space, how can we? Just like for graph coloring problem, we know the value may be 1, result may be 1, 2 up to 8. Here similarly, we'll show this is the solution space, then we'll apply prune and search. Binary search is a pool and search, pooling factor is half. Here also we will apply pool and search technique, where pooling factor is 1/4. Right? Now, what is the decision problem? And this is the result we have proposed. Order of n plus k, log square n minus k times alpha. Right? And it is also solve that for general k, our algorithm rounds is order of n log square. And this algorithm is not beating the existing algorithm. There exists better algorithms for general case. Right? We cannot beat using our this technique. So now what is the decision version? Suppose, because I already told you we know the solution space. So length a particular probable solution of a square can take is known to us. So given a length alpha, does there exist a square of size alpha that encloses at least k points of p? Length is given. That this square is containing k points of p? Right. Now this is your nature of the geometrical. This is the geometric feature. That is, such k square will be either type 1 or type 1 will contain points on the horizontal side and type 2 will contain points on the vertical side. There is a proof. Here we are not presenting this proof. That is, our solution will be type 1 or type 2. We will stick on type 1. Similarly, in similar way, we will be able to solve our type 2 problem. So another observation. For k greater than by 2, our max square, our solution will always contain, for k greater than by 2, a k square must enclose all of this Pn. So this rectangular, this is the Pn. Our solution will always enclose this bounding box. So what does it mean? It has a lot of advantage because it is not required to process all the points lying here. So now what is this? All the leftmost point, all the bottommost point is noted by capital PB, all topmost point by capital P. Similarly, the leftmost point, similarly, the leftmost point PL and rightmost point PL, right? So this is your basically PL. All the points lying on the boundary, right side of this boundary, including this boundary, is noted by capital PR. Similarly, all points lying on the left hand side of this particular vertical line or on this vertical line is noted by capital PL. Similarly, for capital PB, all the points lying below the line PB, including this line. Similarly, for capital PP. Right? Now, this particular result, if you consider, so definitely this particular bounding box has some length and breadth. And if we consider the maximum length and breadth, that is denoted by your lambda. So for alpha greater than lambda, a placement of the square x is parallel square max square alpha, enclosing the maximum number of points from P and enclosing the point set PA can be computed in this. What does it mean? That is, what is my solution? Maybe many number of square. So that particular square will always enclose this particular rectangle. So this point set rather PA here, right? And that can be computed using order of n minus k log n minus k. So when alpha is given, and we are basically doing it by sweep line technique in computational geometry, where segment tree is basically used as an intermediate data structure. A line will be swept, and when a line will be, when you hit a particular point, tree will be updated. And after going on, definitely different type of updation will come, and it will report the maximum number of squares containing by a square whose side, his left boundary is aligned to the point hit just now. So this particular result is proposed using sweep line technique, including using balanced binary tree as an intermediate data structure, and time requiring order of n minus k log n minus. How to get a sense? If you consider the size here, maximum order of n minus k, maximum order of n minus k, maximum order of n minus k, maximum order of n minus k. Right? Total points will tell you that count we can conclude. Right? So now how can How can you solve it? So basically, notice that how can you compute different types of vertical segment? Notice, always you are considering, suppose all the points are in increasing order, P1, P2 up to Pn, including the points PL, PR, PT, Pn. That means P1, P2 like Pn. So P1 to up to what? P1 to PT, P1 to PT plus 1, because the square will always enclose all the points. So we need to consider only all points lying on the line or above the line. That's why P1 is fixed. P1 to PT, P1 to PT plus 1, up to P1 to PM. Why PM? Because maximum point is there. Right? Similarly, for next point P2 again, this part always fixed. P2 to PT, P2 to PT plus 1, PT to PM in this way. So these are the probable vertical distance defined. So now it is required to search among these vertical segments how alpha can be computed of minimum size. For this, we are using prune and search. And I will now go to that particular edge, right edge. So basically, if somebody is familiar with meat finding technique, like cave median, it is similar like this. And it leads to this recursive relation. Tn equals to T 3m by 4 plus order of n minus k log of n minus k. How? Because after getting this vertical distance, we are considering, we are calling it at a particular point. Whether and this length, using this length, it is square, it is possible to compute a k square or not. And since, and binary search, what you are doing? In binary search, what you will do? Tn equals to T n by 2 plus 1. Here, their pruning factor was half. That's why n by 2. Here it is Cn by 3 by 4. So we are pruning 1/4 of the array. Right? So size will be first 1, then 3/4, then 1/4 of 3/4, then 3/4 minus 3 by 16 in this way. And if you add all the terms, it will be converged to a linear state. Right? So if we solve this recursive relation, it leads to n minus order of n minus k log square n minus k. Right? So now why I'm considering this particular problem? Because this particular problem is easy to explain, where less prerequisites on computational geometry is required. We can also explain different other type of problem in computational geometry. That is, here what we are doing, we are so if we go back to this is the main part of theoretical computer science. When we are proposing any algorithm, this is this approach. This is the most important part. We construct the corresponding decision problem. Right? What is the, I've already, when we are constructing the decision problem, our main objective is to solve the original optimization problem. And for combinatorial optimization, beauty is that we know the solution space, but we don't know for which value it will give us the optimum value. This is the hard way. And for which the clever optimization technique is required. Why I have considered this particular problem? This is very easy. So that the pruning technique is right. That is, how can we prune? So that's why now better to call, instead of starting binary search, it's called prune and search, while pruning factor. Right? So, and this is the main challenge. How can you construct the corresponding decision problem? And then definitely we'll call that prune and search, right? Using k square. Now, intentionally I keep sometimes so that, because area is new, right? And so that audience can come, so that they can ask some questions, and I'll be happy to answer them. This is the result. Basically, we are getting given a set of P, given a set P of n points in a two-dimensional plane, and an integer k greater than n by 2, a smallest area axis parallel square enclosing at least k points of P can be identified by order of n plus order of n minus k log square n minus k times using linear space. And this particular technique, which was generally proposed for large value of k is greater than n by 2, can be used to solve the generalized problem. What is that? Given a set P of n points in a two-dimensional plane and integer k less than equals to n, a smallest area enclosing at least k points of P can be identified using n log square. These are the sub-results. It is not better than the existing sub-result. We cannot beat it. And our approach can also be used to solve the problem where the geometric object is rectangle. Given a set P of n points in a two-dimensional plane and an integer k greater than n by 2, a smallest area axis parallel rectangle enclosing at least k points of P can be identified in order of n plus n minus k cube log square n minus k time. Time space is always linear. Now definitely, why are considering square rectangle? Because sometimes this type of algorithm may be used as an initial step for better clustering, where you can start with this clustering, where the object is square, rectangle, or why not circle. And I should stop here. So I'll be happy if you have any questions.
Hello.
Yes, sir.
Am I audible?
Yeah, you're audible.
Is there any questions from the floor? Kundu here. Hello. Hello. Is there any question from the floor or from anybody else? Hello. I think there is no question as of now. Actually, I was having a problem with another computer. I could not introduce Kaushik Majumdar. Shall I do it now? Hello?
Hello. This is Mahapatra. Am I audible?
Yes. Mr. Kaushik Majumdar has received his BTech and MTech degrees in Computer Science and Engineering and Information Technology in the year 2003 and 2005 with a university rank of first class 4th and first class 2nd.
Mr. Subimal Kundu, kindly note. Mr. Subimal Kundu, kindly note.
Yes. Follow.
This tutorial has been given by Professor Priyaranjan Sinha Mahapatra.
Oh, sorry.
Professor Priyaranjan Sinha Mahapatra.
Sorry.
You are mistaken. Please rectify, accurate.
Sorry. I apologize.
No, it's okay.
Please continue. You continue then. You continue.
Thank you, sir.
Okay.
Thank you, Professor Priyaranjan Sinha Mahapatra. Such a nice explanation and nice deliberation. I request Mr. Subimal Kundu, Session Chair, to deliver virtual certificate to Professor Priyaranjan Sinha Mahapatra. Mr. Subimal Kundu, please.
Really, I am having problem with this computer. Let me see whether I can do it again. Try one second. I am having with the two computer systems. The language of the. So I think I will not be able to do it. There is some problem in the computer.
Dr. Anuruddha,
Anuruddha, please go ahead.
Sir, we are very sorry.
No, it's not visible. It is our conference. Don't hesitate. Okay, no, this is not issue.
No, sorry, sir.
No, don't say like word like this. I'm happy. No issue. You have
Such a nice
invited me.
delivery, and we are enlightened with your
Say,
talk.
I'm not able to share it. I can read out. If I can read out, is it okay? I'm not able to share it.
Okay, no issue, sir. You can.
This 66th International Conference on Energy is given with the certificate of Priyaranjan Sinha Mahapatra, University of Kalyani, keynote speaker for 6th International Conference. All the 5% of signature signed there. Gautam Hazra, Aniruddha Nag, Devashish De, Anirban Mukhopadhyay, and Joseph Kumar Mondal. This nice certificate looks very nice, very attractive. The explanation that he has given, though it is very technical, I could not understand much of it, but I understand about his depth of knowledge and his explaining capacity was excellent. I thank you, the audience as well as the speakers. Thank you.
Thank you, sir.
Thank you, sir. Thank you. Thank you. All
Thank
of
you.
you for.
Now I would like to tell you, Professor Priyaranjan Sinha Mahapatra, thank you, sir. And I hope that in every session you will stand beside us like a pillar and make it a grand success.
I'm not able to.
No.
I'm not able to share it.
University and CSI, sir.
Okay, no issue.
I tried to do it.
Yes, there is a button part, there is a share screen option. You just
Yes, sir. Due to some technical glitches, and Mr. Subimal Kundu is quite aged person. He
Okay,
is
no
about-
issue.
It is not going well. I want to keep the certificate with me.
Okay, no issue.
Okay. And now, sir, with your permission, we would like to announce that technical session 1 and 2, which will be run parallelly from 3:30 p.m. to 5:30 p.m. today. Those who are in a session 1, paper ID 11, 12, 26, 84, 92, and 97, and 64, their session